Hello and welcome. Today is March 16th, Monday, streaming live from my house. This will be my first ever stream, so I hope it goes well. Uh, I'll start the day with a question from Mastering Physics, which is due tomorrow. And this seems like a chemistry question, but ultimately it's the same type of question where we're trying to find the total charge. This is problem uh, 19.46 from Mastering Physics number 2. Okay. It says a container holds a gas consisting of some amount of moles of oxygen molecules. 1 in a million of these molecules has lost a single electron. And then it gives you Na. If you don't know what that is, that's Avogadro's number, 6.022 times 10 to the 23rd. You want to treat this number like, just a quantity, a certain amount of quantity, like a dozen is 12 or a baker's dozen is 13. Avogadro's is a ton of muffins. And E is given, which is the charge of your electron, 1.6 times 10 to the negative 19, of course, negative of that. So the formula here is the basic formula where you're trying to find the total charge, Q total, and it's equal to N, whatever number of particles you have, and then times the individual charge, little q. Individual individual charge. Alright, so the total charge must be equal to, in this case, since we have some amount of moles, so whatever your number of moles is, because each mole has a certain amount of, or a certain quantity of particles, in this case being oxygen molecules. So the number of moles times this Avogadro's number, 6.022 times 10 to the 23rd power. Now the unit for this is over mole, and MOL, and MOL is short for MOLE, mole, and the moles cancel, or the units cancel. And of course we'll multiply by the charge of an electron, which is 1.6 times 10 to the negative 19. Now I'm doing positive because we're going to lose these electrons and the oxygen molecules will become positive. And of course we only have 1 in 1 million of these, so I'll go ahead and multiply 1 in 1 million. Okay, so you take your number, multiply by Avogadro's number, multiply by Q, and then divide by a million, and that should do it. So for example, in this, of course your number may be different. Here it says 4.95 moles of oxygen molecules. So in that case I would do 4.95 moles times the number 6.022 times 10 to the 23rd times the charge, and of course this was in coulombs, So I forgot the big C. So the overall unit for capital Q would be C. 1.6 times 10 to the negative 19, and then divide by 1 in 1 million. So 1 million. Okay, and that should equal, I don't know, let me plug it in to wolframalpha.com. 4.95 times 6.022 times 10 to the 23rd times 1.6 10 times 10 to the negative 19, and then divided by 1 million. Okay, so there you have it. And what do I get? I get Q total is equal to 0.477 coulombs. Okay, so that's my number. If your number of moles is different, just change the number in the front. That's about it. If you have any other questions, consider commenting in the YouTube video whenever I upload it. No, but of course send it to me via email, and I will check my email in the mornings at least, regularly. Alright, today I want to talk a little bit about the electric field, and then we'll move on to the activity for the day, which is to draw the electric field lines. So if you pull up your PowerPoint, here we go. So here's the electric field. Alright, so we already covered all of this. This is showing you that the electric field is a vector. It radiates or permeates outwards from positive charges. And of course negative charges are reversed. You should have that in your flippy entry number 3. And this was the picture right below figure 1. This is showing you how you can have a uniform electric field. And so let's talk about that, uniform electric fields. Imagine having a really big charge. And so if I zoom in here around this place, yes, the world is flat. We can say that the electric field is pretty much uniform and constant as long as you're near the surface of this planet, or sorry, of this charge, similar to how gravity is constant near the surface of the Earth. So if I already have an electric field, actually, that's going in some direction. Imagine it like it's a river flowing. Okay, and we always said that positive charges would be riding this wave, riding this river in the same direction as the electric field. So these lines that I'm drawing, the black lines or the arrows, represent the electric field, and the orange ball here, which is our positive charge, that positive charge will feel a force and therefore move in the same direction as the electric field. And remember, the force is equal to the field times whatever the charge is for this plus charge here that we have. Now if instead I had an electron or some other negative charge, this negative charge will feel a force the other way, and it would go against the grain, against the flow of this river, up the waterfall like salmon migrating back home. Alright, anyway, you can have complex or weird looking flows. It doesn't have to be all straight parallel lines. If you have multiple charges, distorts the space around it to where you can have curved lines. And that's what we'll investigate today with our activity. Okay. So in this slide, we have the equation E is equal to F over Q. So force is equal to EQ. To find the electric field, if I know the force on the charge, F electric, I can divide it by Q to get the electric field. And of course the units would be force, which is newtons, N, divided by coulombs, which is capital C, N over C. Okay. There are other units we'll use, especially when we start talking about electric potential. So there is another type of unit, volts per meter, which we can use for electric field. But for now, we'll use newtons per coulomb, which is our normal SI for electric field. Okay, back to the PowerPoint. E has the same direction as F. Since Q is a scalar, of course, F and E are the vectors. So E must point in the same direction of F. F being the force on a positive test charge. And by convention, we just choose Q to be a positive number. Oh, well, we have a comment. Cool. Yes, this is honors physics. I wasn't looking at the screen. Sorry. Yes, this is honors physics. Yeah. Okay. And then after this, I'll do AP1, and then after that, I'll do AP Physics C. And then once this stream records after lunch, so I'll take a break around 12 o'clock. After lunch, I'll start uploading it to YouTube. Hello, Maddie. All right, back to what we were talking about. So E is a vector, and of course my force is a vector. And by convention, we're just going to take the direction of the force is the direction of our electric field, the force on a positive test charge. Okay, so today we want to see how we can manipulate the electric field if we have multiple charges in space. All right, so we know that around a positive charge, the field points outwards in all directions, kind of like the sun. Okay. So this is an individual charge. There's nothing around it, and it's in space, it's empty, etc. And we know that if we had a negative charge, all the arrows would point inwards. And they point inwards, remember, because this is the direction my positive test charge will take if it was at that spot in space. Okay, now if we combine these two charges right next to each other, so instead of being separate charges out on their own, I'm going to go ahead and put them together now. So if I have a positive charge next to a negative charge, remember the arrows come out of the plus and into the minus, and this is basically what we're doing with our activity today if you download it from Canvas. The arrow that points to the right here will eventually go into this negative. And so instead of drawing just two separate arrows, I'm going to draw one single arrow that goes out of the plus into the minus. Ooh, I don't like this. Let's go and try ink to shape. Ink to shape. Ooh. Ah, no. Again. Nope. Come on, ink to shape. There we go. Why is it smaller? I don't like it. Okay, that's good enough. Plus, minus. So again, the arrow that comes out of the plus. Hello, do you take notes on it? Yeah, you should take notes on it. And of course, you can always rewatch the video Whenever Twitch, well, whenever I stop the stream on Twitch, you can go to the video section and then you can always rewatch it. And then, of course, I will also download it and put it on YouTube. Alright, anyway, so this positive charge will send an electric field vector to the right, and essentially that vector combines with the one that's supposed to go into the minus. Right? Ideally, you use a ruler and make it straight. So let's go and do that. So it'd be a nice straight arrow. And so when you do this with your activity, make sure you use a ruler. Okay. All right, and one thing to note is that these arrows, they kind of combine, and they don't actually intersect. The arrows represent, they're not real, but they represent the direction of the force a positive test charge will take if it were at any spot along that line. So imagine putting a little tiny positive test charge here, and if I did that, based on the arrow that we drew with this orange arrow, which represents the electric field, this orange arrow tells me that this positive test charge will move to the right, or feel a force to the right. All right. Next, we have some arrows. Now we know that one of them goes diagonally upwards to the right. Let me turn everything to shape. There we go, to the right. And we also know that there's one for the minus charge that goes diagonally downwards that way. And so those two will combine and then create a nice parabola that goes up and then back down. Okay. We also have one that goes downwards to the right from the positive, and there's a matching upwards to the right on the negative charge. And so those two combine, create a nice parabola that go into, okay. All right. And now the ones that are supposed to go upwards and straight downwards will start to bend and curl. So there's more and more and more. It'll go higher, but eventually come back down again. And you can see these pictures in your book. Yes, your book. This should be in page 714. So if you go to page 714, you can see these pictures. All right, anyway, it goes further down and then into. Okay. Even the ones that are supposed to go upwards to the left and downwards to the left, remember there's a symmetric inwards for the minus charge, and these two, yes, even though it doesn't look like it, will go around, will bend, and then it will go beyond my screen and then come back down again here. This one too, this one will go around, go further down, and then come back and meet up with its partner on the other side. Basically it's going to look like a frog face or something. Whoa. I like this one. There we go. And this downward one will come in. All right. I'm going to switch to a I'm going to pull up a simulator, and while I do that, let me switch the screen. Okay. let's go back. So I'm going to the PhET simulations website, and then if I pull up the physics, there is a nice electric field simulator, and eventually we'll use this. Fields and charges, let's go and play. Alright, so as soon as I put a positive charge, kablamo, and it shows you all the arrows around. I'm going to place it right in the middle here. If I used a negative charge instead, so let's use a negative charge, and all the arrows point inwards. Whoa. Now you can see how the arrows near the charges are brighter, and the arrows that are further away, those are not as bright. They're dimmer and dimmer. That's to represent the magnitude of the vectors. So the further out you are, of course, the weaker it is. Yes, please take notes. Alright, and so you see these arrows that are darker, of course they're weaker. Right, now the sensor, this thing, shows you, which way. This is the test charge. This is a positive test charge, and this is how we, this is how we found the direction of the electric field in the first place. And so when I put the test charge here, it points to the left. Of course, as I go out, you see that the arrow, the force vector, decreases, and if you're at infinity, you'll have zero force. But of course, you have to be infinitely far away from everything. The closer I get, the stronger this force vector is. And as r decreases, when you decrease r and it gets closer and closer to zero, the force becomes almost infinite, or I guess infinite. And it just destroys the simulator. Whoa, laser beams. Zoom, zoom, zoom. All right. Now to put two charges together, I'll put the left one here, and the positive one right next to it. Okay. Remember, it comes out of the plus and then it goes into the minus. There you go. Out of the plus and into the minus. Okay, so as you can see, arrows are going upwards, so they curve, and then they go back down into the minus. Yes, even the ones that are going all the way to the left eventually go out all the way to negative infinity, wraps around the entire universe because it's a bubble, I guess, and then comes back down. Now, there is no, assuming that the universe is infinite, if it is, then the arrow just keeps on going forever. If it's not infinite, then I suppose it would come back. This arrow doesn't necessarily have to be the same line. It's just along the same axis, and it's coming back in. Again, the arrows just indicate which way a positive test charge will go if it was at that spot in space near these two other charges. Okay. As you start adding other ones, it gets more complicated and more complicated, and so you get these wavy patterns. These wavy patterns are what you saw in your PowerPoint slide. If I go to the PowerPoint slide screen, PowerPoint, there's our PowerPoint. So this slide here, see how the lines are curved? So you get curvy lines by having multiple charges in space, and so as the field vector or the vector arrows go out from your positives, they'll try to go towards the closest negative, and you can kind of bend the river, if you will. But again, if your test charge is in that field, even though it's curvy, kind of like a roller coaster, it'll just fall. It'll feel a force. It doesn't necessarily have to move exactly as the arrow is drawn. That's because as it gains velocity due to the force, it still has momentum, and therefore whichever direction that momentum vector is, it'll try to go in that direction. Newton's first law, object in motion stays in motion. But the new direction of the electric field will change the direction of the force on it. So if you have momentum that is pushing you, or if you have momentum that is taking you to the right, but now you have a force that is downwards. What will happen is that yes, you're going to go to the right, but you will accelerate downwards, creating a parabolic trajectory. All right, back to OneNote. There we go. Okay, so let's see. If you go ahead and go to your canvas, you should be able to download this file. I put up both the PDF and the Word doc file. You can do whatever you want, you can choose whichever one you want to use. Let's see if I can draw pens. Okay, so the easiest way to do this activity, of course, use a ruler. Oops, undo. Okay, use a ruler. It says to draw electric field lines with at least 16 lines from each charge. Again, the easiest way is to start dividing the charges up, multiples or 4 at a time, and then doing it on the opposite end. So using like a north, south, east, west. So we'll start with up, down, left, and right. Oh no, how do I do this? Undo, draw, go away. Pen. There we go. So I'll draw a line, draw a line. So that's 4, and I need to have 4 symmetric ones on the negative one as well. Okay. What you do is dotted lines, so that you can connect. Okay. Oops. Let me shrink it a little bit so you can see everything. There we go. All right, and the ones that go straight down will curve a little bit. Okay, I hope you guys can do it a little bit better than I am doing right now, because I have too many things around me to get this stream thing working. All right, so this upward one, we'll go ahead and curve upwards. Oh, it's so hard to write. There we go. And then downward one will go down. Okay. And of course the left one goes left, and then the right one goes right. Oh, sorry. The left one goes left and then comes around, wraps around the universe, and then comes back into the minus. So they do have direction. Okay, remember they point out of the plus and into the minus. Next up, you want to subdivide these 4. So go at angles, 45-degree angles, so you can get, so this is only 4 lines. We're going to do 4 more by dividing this. 1, 2, 3, 4. Now we're at 8, and then we will subdivide this again, and that'll get us to 16. So let's do the 8 first, so 4 on the other side. Okay, let me erase that. There we go. So we're at 8 lines right now. Okay, the one that shoots off at a diagonal, go up and then back down, downwards to the right, down, like so. Upwards to the left will go upwards, but eventually it'll start curving like this. Upwards, curving, like so. Like so, and so. Okay. So we have 8 lines so far. And finally, if you subdivide it one more time, go in between the lines, that'll get you to 16. So if you start from here, that's one, two, that wasn't very good. Let me try again. One, two, three, 4, 5, 6, 7, 8. So by going in between, so I get 8 more lines. That gives me to 16. And that should be the end. Oops. We also have to do it on the minus. So let me activate pen. There we go. 1, 2, 3, 4, 5, 6, 7, 8. So that's 16 and 16 on both. The trick is to connect them all. So the one that's inside will go down and back in. Remember, there's always a partner on the other end. Alright. And the ones that curl will just curl in between. Curl. 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 And then in betweens again, they extend outwards more than the one below it. So this one extends outwards more than the one above it. Here we go. This one will curl. And this one will curl. Alright, that's it. If you can't hear, restart your browser app. Can you hear me? If anyone can hear me, please type in the chat. Oh, okay. Cool. All right. Oops. Let me undo that. Oh no. Changing screens. And it's all gone. Excellent. That's... Well, because it's a video, you can always... you can always go back. I messed up somehow. So I closed my file without saving. And now it's all gone. But anyway, when the VOD is up, please rewatch it. Or, yeah, it's an L, sorry. Now for plus and plus, remember this is repulsion. We saw that the plus and minus, which is attraction, that's what attraction looks like. Something like this. The field lines kind of converge, and so the space around it is distorted. And it goes into the minus, pushed away from the plus and into the minus. Next, what we'll do is the plus and plus, and of course minus and minus is very similar. The only difference is that, hey, Slazer, I know that name. That's Shiraz. Or is it S Laser? All right. The plus and plus will repel each other. So if I go to my simulator, let's put these charges away. So we'll put this plus charge here, and put another plus charge here, and it's not very good, is it? That's good enough. What you should notice is that at the middle there's this vertical asymptote, and directly at the center the arrow disappeared. That is to show you that the electric field is 0 when you're in the middle between two positive charges, and it could be two negative charges as well. Directly at the middle, the electric field is 0. This only happens is if the charges are equal. Can you go back to the first part of the worksheet? I missed it. Oh no. Well, Maddie, the good thing is that you can rewatch the VOD and see how I did the first part. Because somehow I closed my Word document and it lost everything. So once the stream is over, you can go to the video section and then just rewatch it. I'll also have to download this video and then we'll put it on our YouTube channel. And then if you go to the main page on our homepage, Z Physics, you can watch the video there as well. But I think Twitch lets you see streams at least for 14 days. I think whatever I'm streaming, it'll be up for 14 days. You can't hear because I'm screen sharing, Casey. Oh. Well, after I end the stream, you can go to my profile page and then click on videos, I guess, and then you can watch it there as soon as I end the stream. All right, so Maddie, maybe doing the next one. We'll do the next one, and maybe you can figure out the first one. The first one should look something like in our notes this thing. So out of the plus and then into the minus. So the second one. Okay, let's do it on notes first. The second one, ink to shape. Here we go. So oops, that's not very good. Yeah, there we go. All right, it's a little small. There. So if I had plus and plus, again, minus and minus will be similar. Plus and plus. Okay, the first thing you do is go directly at the middle and then draw a vertical asymptote. So let's do a 90 degrees. And then I think this is the middle. So I'll do a vertical asymptote here. And the lines will curl. Now, the initial vectors that are just next to each charge still exist. So directly at the center, it does exist. So, oops, let me try this again. I want to get it directly in the middle. All right, so I've drawn some vectors here. Okay, this one points to the right, right, and the vectors are decreasing in size to show you that they are weaker and weaker and weaker. And of course, directly at the center, it's just a dot because they cancel each other out. Each individual charge has its own electric field vector, kind of like the force vectors we did last week with FAB and FAC, all those things. So now it's just an electric field vector. And so the field vectors cancel out directly at the middle because the charges are the same and we're equidistant from both. Okay. So again, we're going to take the same approach, divide it into 4 first. So we got the right ones. And then we'll do up, down, and left. And then up, down, and left. Like so. Oh, question. Does Global Protect block Twitch? Type in chat if you can answer that. All right. Let's see. So we have 4. And these ones will bend slightly away, like so. Bend away, like so. Anyone out there? if you let me know if Global Protect bans Twitch, and then we'll see what we can do about that. Anyway, upward one bends away, downward one bends away, like that. Global Protect does. Oh, okay. Yeah, that's what I thought. So, I guess only people who are using their own computers can watch for now. Once I upload the video onto YouTube, I can unblock YouTube at least through Global Protect, and then you can watch the video on YouTube afterwards. So expect the video to be up on YouTube around 1 o'clock or something like that, around 5th period. All right. So first period people, you guys just have to wait until 5th period physics. And the ones that go left will just keep going left. The ones that go left keep going left, or to the right will go right. All right, next up, divide this into 4 sections. So in between each line, you're going to go halfway. So 1, 2, 3, 4. 1, 2, 3, 4. Can you use your phone for Twitch if you want? Oh, yeah. Oh, you can use your phone. Yeah, sure. And there is a Twitch app, I suppose. Okay. All right. The one that goes upwards to the right will curve. Okay, and remember asymptotes, so you don't actually touch them. They just go out towards infinity. And same thing on this other side. They'll go out towards infinity. The downwards one will go out downwards towards negative infinity. And this one will go downwards towards negative infinity. Okay, try to make it as symmetric as possible. The one that's supposed to go upwards to the left will curve a little bit. Downwards to the left will curve. Let's go and curve the other one. And curve the other one. Alright. Next up, we're going to subdivide again. So currently we're at 8. We'll go in between the lines, and that'll get us to 16. So 1, 2, 3, 4, 5, 6, 7, 8. Alright, do the same thing on the other one. 1, 2, 3, 4, 5, 6, 7, 8. All right, now we just follow the tracks and just bend away from each other. So this one will bend this way. This one will bend this way. This one will bend this way. This one will bend. More bendy. More bendy. Okay. Hey, we have 14 viewers, man. I'm guessing people are still sleeping in. Well, actually, I mean, I only posted this on Twitter, so if you're not following us on Twitter, consider following us on Twitter at ECR_physics, so you can stay up to date on all physics-related content. All right, so that should be the second one. Go and finish that up, and then upload it into Canvas. And as far as PowerPoints are concerned, so we went through this. All right, this next slide here is showing you that if you have multiple charges, why don't I? Actually, I'll just pull it up on my OneNote so I can actually write. If you have multiple charges, then the lines converge with each other. So let's see, draw pens. Okay. Okay. So of course it comes out of the positive and then into the negative like this, right? Now all positives have a slight deflected ones that go, downwards to the right, I suppose. But at the same time, this other charge also has a downwards to the left, and these two vectors will add up. Notice how their components, there are two components, or one of the components will cancel, leaving you with the net resultant vector to be straight downwards like this. Okay. So essentially, if you line up a bunch of charges together, the field in the middle points straight. So this is what we call a uniform electric field. This is a uniform or constant. I'll use E with a vector symbol here. E with a hat. Well, it's not really a hat, but VE with a half arrow. And that'll be the electric field. Okay. So let's see if we can do that with our charges. Let's use minuses. So I'll put a row of positive charges. Boom, boom, boom. Oh, look. And then put some negative charges. Boom, boom. Okay. They're not perfectly aligned, but you can kind of tell if they were, it would be better. How the inside or in between has straight lines. Now, of course, outside you get some curly lines, but we're not really interested in the outside. But at least in between, we have a uniform electric field. So by putting a bunch of little charges together, we can kind of simulate the same thing we were talking about at the start of today's lecture, is that if I had a big giant charge, and if I was near this big giant charge, near the surface of this big giant charge, we would have a uniform electric field. But it's, pretty much impossible to have a charge like this. So we can do the same thing by lining up a bunch of little charges together. Okay, we're teaming up together. Plus, 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 minus, 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 and this will get you a uniform electric field, similar to being next to a big giant charge. All right. The idea of electric field changes the way we view space. Blah, blah, blah. Make sure you copy these PowerPoint slides down up to this equation. So this is the other equation. We know that E, of course, is equal to the force divided by the charge. Okay, that's good as long as you have the force and the charge. But E, if I just have the charge and I don't know what the force is, however, I know how far I am, some distance r away, we can say that the electric field at that spot is equal to K, same K, 99, times the charge, this charge here, Q, divided by distance squared. So remember, force has two Q's, K, Q, Q, over r squared, but the electric field has just a single Q. The electric field represents the strength of the field away from just a single charge at that spot in space. Do we put it on OneNote or on our Flippy book? No, this is all regular notes. Follow your calendar, right? So if you follow your calendar, Monday, today is not Flippy Day. Flippy Day was on Friday. So the stuff that you wrote down on Friday should be going into your Flippy. Let's see if we can do a... Ooh, cool. How do I... This is... Oh. Pog. What is Pog? You know, Pog was actually a game. I think when I was in elementary school, there used to be these disc thingies that we collected. Well, I didn't really collect it. I just these disc things. I never knew what you actually did with them. I guess you hit them or something. Trying this problem. Ooh, a quick basic question, a quick plug and chug. It says at a certain location in space, a positive test charge Q prime is equal to 2 times 10 to the negative 5 coulombs experiences a force of 0.80 newtons at an angle of 40 degrees. Find the magnitude and direction of the electric field at that point. All right. So so we know that we have a positive charge. Just look at the number. Whoa. Hey there, bud. That's a name that we should not use. I'm still Mr. Z to you. Alright, so we have a positive charge. And a positive... at a certain location, a positive test charge Q experiences a force of 0.80 newtons at an angle of 40 degrees. There you go. Teach this youngster some manners. Alright, so we're going upwards to the right at an angle of 40 degrees. Okay. So we're given the force, we're given the charge. So to find E, we're just using our first equation, some plug and chug here. E is equal to the force divided by the charge. So that would be 2 times 10 to the negative 5th coulombs divided, newtons, not coulombs, newtons, divided by the 0.8. Looks like there's 2 sig figs, so we'll keep it at 2. No, this is way off. Oh my gosh, I'm so bad. I need to go eat breakfast. Force is 0.80 newtons. There we go. Divided by 2 times 10 to the negative 5th coulombs. Alright. So, of course, the magnitude part is pretty simple. It's the plug and chug. I guess the direction might be a little confusing. Yes, there's no arctangent or anything. It's actually much more conceptual. Alright. And if you look at the equation, you see that E is a vector, and we know that force is a vector. The 40 degrees is the direction of the force, so this is the force, and we're using the force to find the electric field. And since these two sides of the equation have to be equal, the direction of the force must be the same direction as the electric field. Therefore, theta is 40 degrees. Alright, it's been an hour. I think that is enough for today. You should do your Mastering Physics, which is due tomorrow, Mastering Physics number 2. If you have questions, send them to me, and then we'll have some time at the start of tomorrow to go over them. And then, and do your electric field drawing. The electric field drawing is due Saturday midnight on Canvas. So draw it just like we did today. Discard. Here's the answer, 4 times 10 to the 4th. You should draw it similar to how we have it in our notes. So something like that. Alright, I guess that is all. I'll see you next time. Bye-bye. Oh, by the way, AP1 will start soon, around 10. I'm gonna go get some food, and then I'll post an actual schedule, so we can do this around the same time every day. So I am thinking of doing honors in the morning, like 8 to 9, and then we can do AP1 from 10, because yeah, and then we'll do C all the way at like 11, around third period. All right, see you later. Bye bye.